to model projectile flight. At this time in my pre-calculus classes, we are learning how to use polynomial functions to model real-world situations. And one of those situations is modeling what we call projectile motion. And this graph function represents the height of an object in meters dependent on time and seconds. And the meaning of the function is that this object, maybe a football kicked in the air, or a rock thrown upward, or something else, moves initially at a rate of 24 meters per second, and that's the meaning of the 24x in the function. And as time goes on, after 2 seconds, the object reaches a maximum elevation of about 30 meters. And later, nearly 5 seconds after being launched, the object reaches ground level again. So this is an example of how a quadratic function is used to relate altitude, elevation, or height as dependent on time. But quadratic functions can be used to model something else, something quite obvious. They can be used to model the path of the object being launched. And arcs formed by projectile motion form parabolic arches like this one. The size of the arch depends on the initial velocity of the object being launched or fired. However, the shape of the arch depends on the angle of incidence at which the object was launched or aimed. We call this the angle of incidence, and here's a drawing showing two different angles of incidence, one of 30 degrees up from horizontal and one of 60 degrees up from horizontal. In launching an object, we can take a close look at an initial angle of incidence. Now this blue ray designates the initial firing or launching magnitude and direction of the object. Now to analyze this direction and magnitude, we will measure the drawing of the ray against the coordinate grid shown here. And the coordinates of this vector are 5, 11. And there are other notations available to show that a line segment is a vector. I've seen it in angular brackets like this. A vector has two attributes, magnitude and direction. In fact, that's a definition of a vector. It's a quantity that has both magnitude and direction. Magnitude is another word for length. And on a coordinate plane, it has another definition. It's an ordered pair whose geometric representation is an arrow. This vector can be separated into vertical and horizontal components. The vertical component is 11 units up, and the horizontal component is 5 units to the right. To find the size of this magnitude, we find the length, and to do that, we can use the Pythagorean theorem. So we would find the magnitude by taking the square root of quantity 5 squared plus 11 squared, and that's a little over 12, about 12.083. If we knew the angle of incidence from the horizontal, we could use trigonometry to rewrite our vertical and horizontal components of the vector. The angle of incidence happens to be about 65.556 degrees. I found this angle by taking the inverse tangent or arctangent of 11 over 5. And now with a magnitude of 12.083 and an angle of incidence of 65.556 degrees, we can rewrite the vertical and horizontal components of our vector as follows. The vertical component is 12.083 times the sine of 65.556 degrees, and the horizontal component is 12.083 times the cosine of 65.556 degrees. Now we get to Mrs. Cooper, our physics teacher. This is the exercise she had for her classes. There is an Angry Birds theme in the exercises. And these are the goals for the lesson. I will be able to identify the variables in a kinematic equation. I will be able to resolve the velocity vectors. I will be able to calculate the time and how far a projectile launched at an angle ends up. And then she follows up with why this is important. 1. Not everything moves in only horizontal and vertical directions. 2. Learning about projectiles is important because from trying to get a basketball through the hoop to missiles being shot, projectile motion plays a role. Situation number 1. An angry bird is launched at 7 meters per second at an angle of 20 degrees north of the horizontal. How long is the angry bird in the air? What is the maximum height the angry bird travels? What is the range? Before doing a full analysis, I would like to examine this last question, what is the range? In algebra, range means the values, all the values of the dependent quantity, which would be the height of the bird, and it would be greater than or equal to 0 and less than or equal to the maximum height of the bird. But in ballistics and trajectory language, the range is the horizontal distance traveled by the projectile. And in this lesson, we'll be using the second definition and not the classical algebra definition. In other words, the definition is how far the thing travels in the air horizontally. The first thing we'll do is draw the vector. The magnitude of the vector is 7 meters per second. Let's talk about what is really happening here. Just looking at what happens vertically, the vertical component of the vector makes the bird go up, and the force of gravity brings it back down again. Here's the bird at the start ready to be launched. Here it goes vertically at first. From the vertical component of the flight, we were able to determine two things: the time in the air and the maximum height. Next, we'll bring in the horizontal component along with the vertical component of flight. Here it goes. Here it is, having traveled all the way. Now we'll use trigonometry to separate the horizontal and vertical components of the vector. The horizontal component is 7 meters per second times the cosine of 20 degrees. And the vertical portion of the vector will be 7 meters per second times the sine of 20 degrees. Now let's ask ourselves the question, why is it helpful to separate the launching velocity vector into vertical and horizontal components? The reason we do it is that the horizontal and vertical motion operate using different rules. The vertical component has to take into account the force of gravity, while the horizontal component does not. In units of meters, the vertical elevation will be determined by the function d sub v equals negative 4.9 times t squared plus 7 times the sine of 20 degrees times t, and the independent variable t represents the number of seconds since launching. And the horizontal component is d sub h equals 7 times the cosine of 20 degrees times t. In the function, this number, 0.342, is the sine of 20 degrees. And with the graph, we can answer the first two questions. The time in the air looks to be about 0.5 seconds, about half a second, and it looks like the maximum height is about 0.3 meters. Now I'll use the analysis features of the calculator to get to these numbers more exactly. We get a time in the air, more precisely, of 0.4886 seconds. And we get a maximum height of about 0.292 meters. And using the horizontal component of the vector with our time in the air of 0.4886 seconds, the bird travels about 3.21394 meters before hitting the ground. So that's our range, about 3.214 meters. So we have our three answers. The time in the air is about 0.4886 meters. We have a maximum height of about 0.292 meters, and we have a range, or distance traveled horizontally, of about 3.214 meters. Now we'll get to situation number 2, another very similar problem, but with an initial launch velocity of 14 meters per second and an angle from horizontal of 80 degrees. I now invite the viewer to stop the video, then solve the situation, then restart to see if you got it right. Here's the graph of the function showing the height of the dependent variable as the dependent variable and time as the independent variable. The time in the air is 2.813737 seconds and the maximum height is 9.698468 meters. And based on a time in the air of 2.813737 seconds, the maximum height is 9.698468 meters. And the range of flight is 6.8404 meters. Now we'll get to situation number 3 with an initial launch velocity of 7 meters per second and an angle from horizontal of 45 degrees. I'll not be working this one out, but plan on having the answers in the description of the lesson below. I hope this introduction to using vectors to model projectile flight has been helpful. This has been Using Vectors to Model Projectile Flight. Thanks for viewing.